Hello, everyone. We will begin the webinar in approximately 1 minute. Morning, and welcome to Parker Hannifin's webinar presentation entitled A Brand New Approach to Understanding and Mitigating Stress Corrosion Cracking and Hydrogen Embrittlement. My name is Greg Troutline. I'm the publisher and editor of Offshore Engineer Magazine and oedigital.com. Leading the discussion today are a pair of industry experts from Parker Hannifin, Dr. Paula Lepore and Dr. Anshul Gowda, who will guide you through SCC and HE fundamentals and impact on material integrity, recent advances and real-world case studies, novel testing and evaluation techniques, effective mitigation strategies, and future trends in corrosion control. Without further delay, I'll hand you over to Paula and Anshul for the presentation, which should last about 40 minutes. Following the presentation, we welcome all of your questions and encourage you to use the Q&A box in the Zoom interface to ask them. With that, welcome Paula and Anshul.
Thanks, Greg. Good morning, good afternoon, and good evening, everyone. Conventional austenitic stainless steel grades, such as 316, 316L, have served as alloys of choice for several years for energy markets, including our conventional oil and gas. With the advent of clean technology and new alternative fuels and hydrogen, these applications see increasingly more corrosive environments and critical ranges of pressure and temperature. This has often led to more frequent and more severe corrosion attacks, especially those related to stress corrosion cracking and hydrogen embrittlement. These two corrosion mechanisms are categorized as two different types of environmentally assisted cracking. So today, under SCC, we will explore further the chloride SCC and sulfide SCC, whereas under the hydrogen embrittlement, we'll focus on embrittlement caused by H2 rich gas environments and H2 plus H2S, more commonly known as sour surface. Why are we focusing on these types of corrosion? Stress corrosion cracking and hydrogen embrittlement are not easily identifiable in the field, and they can cause sudden and catastrophic failures. There is an increased risk for personnel safety, potential for leaks and spills, downtime, expensive repairs, replacements, and reputational damage. Why should we monitor closely? Oil and gas structures and components, they are exposed to H2S, CO2, chlorides, caustics, overall sour environments, cathodic protection, welding, high pressures, temperature gradients, residual stresses caused by welding and fabrication, for example. But overall, corrosion costs a lot to our industry. In a recent study published by MPP for NACE, we know that these numbers go as high as 2.5 trillion per year. However, we'll show you here that there are some simple ways to monitor and manage these types of phenomena, saving us up to $875 billion per year. A very interesting example that all of us know is the Deepwater Horizon case study. Although the main cause of the accident was not caused by corrosion, the buckling, the subsequent buckling of the BOP and the spill itself was definitely deteriorated by the SCC and hydrogen embrittlement of several boats, tubing, and pipes. One other example close to the clean tech world is a PAM electrolyzer, where parts are submitted to high concentration of caustic media at high temperatures, showing accelerated degradation, sometimes as quick and as fast as 48 hours of operation. This is a classic example of stress corrosion cracking or caustic SCC. Yet another compelling example in the energy market is the hydrogen embrittlement of components of a gas turbine, where hydrogen embrittlement was caused by contamination of the media or deionized water, where combustion gases were being backflushed through the hydraulic circuit, causing premature failure. So now that we've set the stage for these types of corrosion, let's discuss in more detail the three requirements for SCC and HE to set in. Basically, SCC and HE will only happen if three components are present. These components are tensile stress number 1, corrosive environment number 2, and susceptible material number 3. If those three requirements exist with time, fine cracks will form, and if left unchecked, failure will occur. So talking about the first pillar for SCC and HE to set in, tensile stresses, they are directly proportional to SCC and HE. Tensile stresses come from a combination of effects that the component will be subjected during service life, from raw material forming to machining to heat treatments, cold work, assembly, installation, operation, etc. Now, the second pillar is touching the environment. The more corrosive the environment, the more critical the issue. The environment will ultimately dictate the corrosion mechanism. Requisites like higher temperatures, relatively high concentrations of chloride, sulfide, H2S on wet environments are critical. For example, when you think about a typical offshore environment, it has chloride concentrations at 19,000 ppm. And it's been proven by testing, lab testing, that conditions with concentrations as high as 2 ppm of chloride at 390 Fahrenheit or higher as 100 ppm at room temperatures will cause stress corrosion cracking and hydrogen embrittlement. This proves how susceptible most systems are to these mechanisms of corrosion when submitted to a typical offshore environment. Talking about the third and last pillar here, materials can be more or less susceptible based on its microstructure and chemistry. Issues like sensitization that you see here on the second picture on the left, big inclusions, you see the picture down below of 316 with big sulfide inclusions, or large amounts of ferrite, carbides, and nitrites or sulfides. Like the first picture there, where you see a super duplex with dark phase. These can be highly deleterious, and they will definitely accelerate the process of stress corrosion cracking and hydrogen embrittlement. One other interesting way to look at the material is how should we select the proper alloy based on its nickel content. Here you see the Copson curve and the stress corrosion cracking valley of susceptibility. This curve will plot the effect of nickel content in a ferrite for ferrite nickel chromium alloy coupons under stress, subjected to a boiling magnesium chloride solution, or simply the STM G36 testing. The Copson curve shows in the very bottom there more susceptible materials to stress corrosion cracking, such as 304, 316, 316L. On the right side of the curve, the content of nickel that actually has a positive effect to the stress corrosion cracking resistance, it's only for numbers beyond 20%. This is the reason why we are forced to select higher alloys for critical applications, such as 6MO or super duplex, for example. All in all, the most important takeaway here is that adding a couple more percentage of nickel will only give you marginal improvement to stress corrosion cracking. Ultimately, chemistry is not everything when selecting your material for a specific application. Other factors need to be taken into consideration. Now, I'm going to hand to Anshul to talk a little bit more about types of corrosion.
Thank you, Paula. So thanks for setting the stage and giving us a brief introduction to the common elements of the different forms of stress corrosion cracking and hydrogen embrittlement. Next, we are going to talk about some of the ways we can distinguish between the different types of corrosions that we are dealing with today. Okay, so first off, there are a lot of agreements as well as disagreements within the literature about what is the exact mechanism for each of these forms of corrosion. One of the major ways of distinguishing between the different forms of corrosion is by looking at how does the crack propagate and appear in the microstructure once we mount the sample and etch it using the right etchants. If the crack is intragranular, in other words, if the crack is cutting across the grains, it is typically a very strong indicator that you're dealing with chloride stress corrosion cracking. Another big hint can be where was the application installed? Was it near shore or offshore, or maybe in a hydrogen-rich environment? Yet another big clue is what material has undergone the cracking. Is it a stainless steel? Is it a high-strength steel? Is it some other alloy? All of those show propensity to develop stress corrosion cracking using different mechanisms. And lastly, another big clue is the temperature at which the corrosion is occurring. So all together, one thing that is common with all forms of stress corrosion cracking is that you will always see branched cracking. That is probably the biggest clue that one can have as an end user to detect that we have a stress cracking or a hydrogen embrittlement issue. So let's talk about each of these forms of corrosion in a bit more detail. Chloride stress corrosion cracking is perhaps the most common form of stress corrosion cracking observed in offshore environments. What is happening here is the chloride ions, which are abundantly present in the environment, they attack any weakness in the protective chrome oxide layer, which is actually responsible for giving the corrosion resistance to stainless steels. So essentially, whenever we have any surface inhomogeneity in our material, such as a pit or an inclusion which is exposed to the environment, or any contamination that has settled on the surface of the metal, the chloride ions are very good at picking that weak spot and actually attacking it in such a way that an anodic reaction starts occurring on the metal surface, which leads to dissolving of the metal ions. And that eventually leads to stress concentration increasing in that local area, and that ultimately leads to cracking. And even after the cracking is initiated, this dissolution continues and the crack just propagates freely. This is what a typical chloride stress corrosion crack would look like, where you have the branching that I spoke of earlier, but also notice that the nature of the crack is intragranular, and because the cracks are cutting across the grains. we have a view here both of the microstructure as well as of the fracture surface of such a crack. While there are several ways of testing for chloride stress corrosion cracking, the most common chemical test that is applicable to offshore alloys is the ASTM G36, which is a boiling magnesium chloride test, which can be done both in the form of coupons or with slight modification to the test. It can actually be done in finished parts, but only by very highly specialized labs. The other common method of testing for chloride stress corrosion cracking is a mechanical test where there is exposure to chloride ions during the test, but also there's a slow strain rate test, a load that is being applied to the material. And this can be a very useful test as well. So we have done some of that modified ASTM G36 testing in our labs. And this is just, in this slide, we are trying to show what are the trends between the different alloys. And what is very noticeable is if you are dealing with an annealed material, such as even anneal 316, the average time that it takes for the part to develop a crack is quite high. Compared to that, for cold work alloys, irrespective of which alloy we choose, we see a dramatic reduction in that time to cracking. Of course, the higher alloyed alloys do a slightly better. However, what is to be noted here is that for most applications, even though this data would suggest that annealed material is the way to go, it puts severe restrictions that we'll talk about later in the presentation, which is why it's not practical to use annealed material all the time. So, that is the cost, or that is the price we pay if we choose to go with annealed material. Our usability of the alloy is hindered. Next, let's talk about hydrogen embrittlement. The basic mechanism of hydrogen embrittlement is basically where you have individual hydrogen atoms that are created close to the surface of the alloy. And those, because of their really small size, fairly easily diffuse into the metal. Once they have diffused in, they can either just come back out, in which case no harm done. However, in some cases, these atoms can actually combine to form hydrogen molecules inside the metal. This hydrogen molecule is much bigger in size than the individual atoms, and therefore applies a ton of stress in the metal right around the molecule. Eventually, this stress leads to the cracking. This is what a typical hydrogen embrittlement crack looks like. While it is possible to have hydrogen embrittlement cracks, both intergranular and intragranular, the more common method of cracking here is the intergranular cracking, which is shown in these two images. So how do we test for hydrogen embrittlement? The way we think about it is there are two individual buckets that we can categorize the testing in. The first bucket deals with how do we charge the alloy with the hydrogen. The second bucket deals with applying mechanical load to see the effect of the hydrogen embrittlement that has occurred in the metal. So in terms of the charging, again, there are two subcategories that we can divide the charging step in. And one of them is where we first charge the alloy chemically with hydrogen and then apply the mechanical load, or we can just introduce gaseous hydrogen at pressure to the alloy and get our charging that way. The mechanical testing can be done in a whole host of different ways, depending on the application and the alloy that we are dealing with. Here we have listed some of the more common ways of doing that mechanical testing. Some of the most common methods that can be employed for offshore testing for hydrogen embrittlement is are ASTM F519 as well as ASTM G148. In the former, we are using chemistry to create hydrogen atoms that are then introduced into the metal and diffuse over time. In the latter, we are applying a mechanical load after that embrittlement has occurred to see how much of an uptake of hydrogen we have had in our alloy, as well as the permeation and diffusion of hydrogen atoms. Next, let's talk about another common form of stress corrosion cracking, which is the sulfide stress corrosion cracking. In terms of mechanism, it is very similar to hydrogen embrittlement in the sense it is also being caused actually by hydrogen atoms that are diffusing into the metal and just forming the hydrogen molecules and thereby causing the stresses. However, the one big difference here is there is hydrogen sulfide present in the environment. This gas is fairly common in offshore applications, especially lately where we are going towards more and more aggressive environments for getting our oil yields. And essentially what happens is the hydrogen sulfide gas acts as something called the hydrogen recombination poison. What that effectively means is in the presence of hydrogen sulfide gas, the hydrogen atoms they tend to diffuse more and more into the metal instead of just combining outside the metal and dissipating away. So with increased diffusion, the rate of the cracking also increases significantly. This is what a typical intergranular sulfide stress crack would look like. In terms of testing, there are a whole host of test methods that have been developed by the industry over the years. And essentially, they are based on the material or the alloy of choice, the environment that we are dealing with, and the application of that particular product or material. Two very good resources for offshore applications that detail the kind of testing available for sulfide stress cracking are the NACE MRO 175 or ISO 15156 standard, or the NACE TM0177 standard. In these standards, there is a lot of detail that is talked about, and they define very well the critical parameters such as hydrogen sulfide partial pressure, chloride concentration, stress strain state, the temperature, different temperatures, as well as different pH of the solutions. So based on the application and the choice of our parameters, the test can be conducted as needed. Next, I'll hand over to Paula to talk about some of the mitigation and prevention issues related to stress cracking. Paula?
Thank you, Anshul. So let's carry on and go back to the 3 requirements that we discussed previously, or prerequisites necessary for stress corrosion cracking hydrogen to set in. We can try to reduce stress, use higher alloys, or try somehow to control the environment, to put simply. So talking about stresses, for example, to reduce stress, we can do several things, but they all come at a cost. We can try to increase the material. We can try to minimize stress concentration and cyclic stresses. We can try to stress relief, mechanical and thermal, but it all comes at increased costs. For materials, we can use higher alloys, annealed alloys, for example, and apply platings or coatings. Often this comes at a higher price, prohibitive lead times, and reduced pressure ratings. And we have very limited control over the environment, of course. All we can do is try to use elements such as corrosion inhibitors, try to operate at lower temperatures if possible, and try to reduce the corrosive element concentration. All this comes at increased cost also in operation downsides. So summarizing all that we discussed about stress corrosion cracking and hydrogen embrittlement so far, it is very clear that these types of corrosion can cause significant damage and are very hard to monitor and control, being called as the silent threat to some of the applications that we're all familiar with. Understanding and identifying the mechanism accurately is key. Being proactive can save lives, but it also can save a lot of money. Prevention and corrosion management is the way to go, definitely. From all the mitigating strategies we discussed earlier, the best is definitely the one that improves performance and is cost effective, but it also should be easily deployed. I'll hand it over to Anshul now to talk to you about a new type of corrosion management technology recently developed by Parker Hannafin. Anshul?
Thank you, Paula. There's been a lot of interesting work that has been done by both academia as well as industry to try and mitigate these forms of corrosion over several years. One such method that we have developed recently at Parker is called the Parker Super Shield. It is a comprehensive corrosion management technology that has been specifically created for cold work 316 stainless steel applications that demand really high stresses or exposure to really harsh environments. Super Shield is the solution that we have launched on our medium pressure instrumentation products to begin with. And it really is applicable to all energy markets related to fluid conveyance at high pressures. Here's a short video about the story of Parker Super Shield. In order to go about developing a solution like that, we went to our customers and listened to them about what their needs are when it comes to stress cracking. And what we found out was we had to have a comprehensive solution that deals with environment, material, as well as stresses that works on 316. Parker Super Shield develops exactly that. In terms of stress corrosion cracking specifically, Parker Super Shield outshines the current 316 options out there in the market handsomely. In terms of the improvement in lab testing, in terms of improvement to service life, we are expecting up to 20x improvement by lab testing. And this is a very significant game changer when it comes to stress cracking. But the benefits are not just limited to stress cracking. We see improvement in other forms of corrosion as well. For example, with pitting, we see up to 50% reduced weight loss. Moreover, on top of it, we also see a better surface finish with this product, as well as significant improvements in hydrogen embrittlement, as well as fatigue. We will be sharing more about that in the future. So what does this mean practically? I shared with you earlier a table where we talked about the performance of the different cold worked alloys and how how quickly they would tend to crack under the ASTM G36 conditions. After Super Shield, the improvement in performance is quite dramatic across the board, even on cold worked alloys. This is important because this enables us to use cold worked alloys, especially 316, and still get remarkable performance, often comparable to higher alloyed options that are currently out there. Another interesting fact is the effect of Super Shield towards sour service type of environments. NACE, now called AMPP, developed a now famous standard, NACE MRO 175, back in 1975 to deal with all the major issues that were happening in the field in sour service. the guidelines that NACE came up with are dependent on the material, the environment, as well as the applications. One of the key ways that NACE tackles the effect of material on stress cracking is by limiting the hardness of the alloys. So for 316, that usually translated to about 22 HRC max. While that worked in terms of prolonging the life towards stress cracking, it also indirectly put a severe restriction on the strength of the material that can be used in such an application. So what are the options that the customers have or the end user has at the moment? We can either go to higher alloyed materials, which can lead to increased costs and lead times, or use annealed materials, which limit the material strength, therefore limiting the working pressures or limiting the use cases for those alloys. Well, with Super Shield, we have tried to give another option to our end users. It is a best of both worlds solution where we can get improved stress crack resistance and corrosion performance. At the same time, there is no derating of any sort needed for these alloys. So we can continue to use the product as it is intended to be used. Paula had earlier shared the Copson curve and how it plots the nickel content with the time to failure in a boiling magnesium chloride type setting. Here we have overlaid the different alloys along with the 316 Super Shield product as well. And what is interesting to note here is the improvement in performance is so substantial that a 316 cold worked alloy can give you a similar performance to another alloy which has up to 30% nickel in its chemistry. So it's really dramatic. And this performance improvement is actually comparable to even super duplex or super austenites that we are so familiar with. One big advantage, additional advantage is also that it is still 316 material, which means there are no chemical compatibility issues or no other legwork needed to qualify this material. With that, I'll hand over the control back to Paula.
Thank you, Anshul. So, what are the key takeaways of Parker's new generation processing technology for stainless steels? Super Shield is a technology that was created for stainless steel materials, yes. But in the future, we plan to expand it beyond 316. It's a technology that is relevant for cold worked or medium pressure applications, really anything beyond 6,000 to 7,000 psi working pressure. It is not a plating or a coating, so it cannot be easily scratched off. It is indeed a proprietary process, or what we call the Parker trade secret. It improves surface finish and increases fatigue resistance significantly. Overall, it delivers 20 to 40x extended service life for your components. That is why it will deliver enhanced asset integrity and operational efficiency at reduced ownership costs, and will be applicable to all and beyond energy markets related to fluid conveyance. Like Anshul mentioned, it will deliver NACE, while it bridges the gap between conventional. Overall, it delivers NACE, while it bridges the gap between conventional and higher alloyed stainless steel materials. What it means that it's a cost-effective solution delivered at very competitive lead times. But all in all, it will deliver safety and reliability. And with that, if you want to know more about Super Shield, We're sharing here a landing page for our white paper with more comprehensive details on the testing and validation for this technology, but also a catalog with parts where SuperShield is already offered. And with no more further ado, I'll open the floor for Q&A. Greg?
Okay. Well, thank you both, Paula and Anshul, for that concise and insightful presentation. And now we're going to keep the conversation going as there are a few questions coming through from the audience. As a reminder, please use the Q&A box at the bottom of the screen to type in your question. And along the way, I saw a couple of the raised hand symbols. We cannot call on people for a back and forth. All questions must come through the Q&A box. So with that, Paul and Anshul, oh, they're coming through quickly now. Okay, I'm just going to start at the top here. How does the time to failure in hours for a boiling solution versus nickel content translate to the material being exposed to ppm levels, and how many years before crack growth?
Yeah, I'll take that, Greg. So it's a very common question when it comes to corrosion testing, that the testing that we do in the lab, how does it translate to the performance in the field? My usual answer to that is it depends. And the reason is the applications are so far varied among themselves that it is very hard to say exactly what an application would entail. However, in the world of corrosion, what we do is we look at trends that are observed by lab testing and then extrapolate those trends to life in the field, as the case may be. And this is usually done best by the end user since they have the best knowledge of the application. So because of that, it's very hard for me to give an exact life in the field. However, the trends should still hold true. And the trends are very clear with SuperShield treatment. The improvement in life to stress crack corrosion is 20x or beyond for standard 316 cold work alloy.
Thank you, Anshul. Can you share more about SuperShield being used on alloys other than 316?
I'll take that as well. That's okay. Yeah, we have shared some data, as you saw, on some of the different alloys that we tested SuperShield on. However, what we see is you still get an improved performance of the same factor in those alloys as well. However, at the moment, the SuperShield product is available only in 316. And, with time, that could change.
Excellent. Thank you, Anshul. Excuse me. Is this coating available in ferruled fittings? Ferruled?
I'll take that, Greg. First and foremost, this is not a coating or a plating, correct? And we mentioned that this is most applicable for cold worked materials. So we mentioned higher pressures beyond 6,000 psi, but there is no reason why we could not apply to what we call the low pressures, 0 to 6,000, 7,000 psi application. It's just becomes more and more relevant as you work with cold work materials. But it's not commercially available for those types of products right now.
Okay, thank you very much. Another one, and actually, to scroll back up. Assume SuperShield complies with both NACE MR 0175 and MR 0103.
No, so the NACE standard specifically says that for 316, it puts a limit on the hardness of the material. In this case, we are not changing the hardness, so we would still use the same technically speaking, it would not comply. However, the point that we are trying to make here is it gives you NACE-like performance because of the process and what we are doing. And that makes it almost like a NACE like performance without actually technically being NACE compliant.
Yeah, it gives you NACE without being NACE.
Right.
Though the hardness is still the same, we're still dealing with cold work material. The performance is alike or better than NACE material with lower hardness.
Yeah, one thing that I would add to that is also that NACE MRO 175. Let's think about what is the reason why that standard was created. It's to increase life in sour service, stress corrosion cracking. That is exactly what Super Shield is doing. So that is why we say it's a NACE-like performance with Super Shield.
Correct. Yes.
Well, thank you both. I have heard of Parker Super Case. Is Super Shield similar, and can you elaborate?
Sure. So yes, Parker Supercase has been a technology that we developed several decades ago, and it has been the gold standard as far as getting hardness on our ferrules and getting the good bite on our connections goes. But this is slightly different. This technology, Super Shield, I mean, is particularly developed for stress crack corrosion. So in that sense, it's slightly different. But when you buy a Super Shield fitting, you actually get the benefits of both Super Shield as well as Super Case, which is done on the ferrule component of our fitting.
And thank you, Anshul. So how does Super Shield stack up to what the competitors are offering in the market?
I don't. So I think the Super Shield like technology, I'm not aware of anything like this out in the market. So it will be hard to compare with something that doesn't exist. However,
Super Shield is unique. It's the process that is unlike anything else that is out there. Significantly improves the overall service life of the parts in the field. And there is really nothing like it as we speak. Anshul, do you want to complete my thought process here?
I've got nothing to add.
Okay.
Yeah, that's okay, because I got to tell you, we have more questions than I've had for any webinar in recent memory, so we're going to have trouble just working through them all. The next one is, can Super Shield be applied in the field? And if so, what conditions are needed to allow for this?
So this is all something that we have been considering, because Super Shield can be utilized for applications such as welded connection, for example. Been working with some of our customers on applications such as PAM electrolyzers, where this is very important. But because these structures are quite big, they need to be accessed remotely, right, in the field. So it's something that we're looking into. Is definitely doable, but it's not commercially available, not yet.
Thank you, Paula. Next one is, since this is not a coating, and I'll say, do you expect cut ends of tubing to have the same properties as the outside surface?
I'm not sure I understand the question. Sorry.
Okay.
Yeah, but this is 316, so we don't expect to see any challenges in this regard. Like I said, you saw the QR codes that we shared previously. If you want to know more detail about the extensive validation testing campaign that we did, years of testing, including assembly, these feedings and under different conditions, to validate just that. I believe what this person is asking, if there's any significant concerns with the biting and leakage issues that comes from utilizing that issue. And a nice segue into that question is that in the future, we plan to offer that to also our valves and tubing also. So completing the triad, so you can have a solution that covers most of the applications offshore for what we offer for medium pressure right now for our product portfolio. So this will be available very soon.
Excellent, and thank you both. And just to be clear, we're obviously this is a webinar and we're answering questions. Afterwards, everyone is going to be getting the presentation and hopefully be connecting with you to answer some of these questions that we might not get to as well. The next one, is there a size limitation for parts that can be treated? We are interested in applying to as welded components. And on that note, can components be welded after the treatment has been applied?
After.
So I can take that.
Yes.
The first part of the question was that they are interested to use it on welded components and whether it would work. The answer is absolutely yes. It could work. We just haven't reached that far yet. We have some preliminary data, but that is still in the works. But the initial indications are very encouraging. However, what I would say is that about the second part of the question is to get the best effect out of Super Shield, it is best if it is done at the end.
After the welding process, correct, yes.
Right.
Again, thank you both. So what is the treated layer thickness of Super Shield, or does it affect the entire thickness of the component?
To put it simply, it varies depending on the parts that you're treating and the parameters of the process for each part that you're treating. So it varies.
Excellent. Next question, and this is a little, not a longer one, but not a coating, what is it? Applied to piping, question mark, tubing, question mark, flanges, question mark, fillings, question mark. Can it be applied to 10,000 meters of 8-inch SS pipe?
Yes, it can. It definitely can. Like I said before, we are releasing Super Shield for one of our key products right now because it's something that we already have voiced to the customer, and they said it's something that they are really looking forward into having first. But there's a myriad of other applications and components that you can apply the technology to. Pipe, flanges, bolts, welded connections, and so on and so forth.
Excellent. Thank you, Paula. So is there a plan to roll out Super Shield to low alloy steels?
Not really, but yes, we need to build a business case for what kind of alloys you're trying to consider or get into. But we thought 316 was a platform that it will give you enough advantages and cost effectiveness in terms of cost, of course, and lead times for most of the applications we deal with on the oil and gas and clean tech world. But yes, depending on what materials you're talking about, it's just a simple matter of applying the same validation techniques and testing as long as there's a business case in place.
Excellent. And thank you again, Paula. Very specific question. Does this apply to 17-4 HH1150? We make high pressure Kelly valves and the balls are made from 17-4 HH1150.
Right, so I can take that one. I'm very familiar with that alloy and that heat treat condition. At the moment, like we said, our target was offshore applications when we were developing this process, and it was also where typically the choice of alloys are 316 alloys, which are cold work. So again, yes, it would be applicable to that alloy. It should work, but we haven't done any testing yet to prove that. And right now, our focus is to launch it on 316 alloys only.
Excellent. Thank you, Anshul. Another specific question, I think this probably goes back to one of your slides, because they're asking, what is the asterisk for in regards to delivers NACE?
Yes, that's exactly what Anshul was explaining about the performance of a NACE compliant material without actually complying to the hardness threshold there. So theoretically, is it NACE compliant? No, but it delivers the same performance of a NACE compliance material. I hope that it's clear now.
Thank you, Paul. I appreciate that. So there's actually a follow-up question, and it says, if it is available on furrowed fittings, is the delivery as long as typical alloys such as 825 and 625, excuse me, which can be 16 to 20 weeks?
No, and that's one of the advantages to Super Shield. It's the cost and the lead times are the same of a 316 type of alloy. So very standard lead times from 4 to 6 weeks, sometimes less.
Wow. Now, can Super Shield be applied on in-service piping, or is it limited to workshop applications?
Well, like I said before, we have a plan to have an option for a field application of the process. However, this is not commercially available yet.
Does Super Shield eliminate the need for coupons and sacrificial anodes in corrosion prevention monitoring?
I can take that. So I would say no. All the best practices that our customers have developed over the years to mitigate corrosion are probably still good to have. The thing I would say that the way to think about this is an additional option in terms of material selection when those decisions are being made in the field. In terms of chemistry, it is 316, but you can expect a much better corrosion performance, and that's the important part. Other than that, whatever other best practices that are being followed, they should be still be continued because they will still have their place.
Excellent. Thank you again, Anshul. Next question. Does the Super Shield process protect the interior of fittings? We have seen issues with salt water getting into the weep holes of autoclave fittings.
Absolutely. So the Super Shield process helps with 100% surface of the product inside and outside.
Excellent, and thank you again, Anshul. Is Super Shield a costly, time-consuming process?
Simple answer is no. It is not costly or time-consuming. It's a process that was developed to guarantee your access to a 316 solution, quick, easy, without much hassle. So that was what we were looking for. And like I said, it took us a year to develop the solution, but we got to a point where it's simple, it's deployed, it's cost effective, and the lead times are very similar to conventional 316 alloys or standard materials.
Thank you again, Paula. I very much appreciate that. So, again, a very specific question. Can you speak to the impact of H2S with WBM water-based mud or formation water creating H2SO4?
I'm sorry, I'm not familiar with that. immunology.
And again, just to reiterate, any of these questions, we'll have contact with everyone. We can knock these out when we're done with this as well.
Right.
I believe.
We can
Go
probably
ahead.
cover the H2S reach environment challenges, right, Anshul?
Yes,
Super Shield is definitely applicable
right.
to help with that.
Right. For a standard H2S environment, it would be very applicable. Basically, the way I would put it is wherever there is concern about hydrogen sulfide being a culprit in the initiation and propagation of cracking, Super Shield would be applicable.
Excellent, and thank you both again. And again, if some of these get repetitive because I'm monitoring multiple screens, you could just tell me it's already been answered. But is Super Shield available on tubing and fittings or just fittings? For very low ppm analytical applications, does Super Shield perform as well as Silkinert?
Right now, we're only offering for fittings. But like I said, there is a roadmap or a plan to quickly introduce valves and tubing and other components related even to regulators and process analytical components that we also offer from our product portfolio. So the answer is yes, in the future, near future.
Excellent. Another question, does it improve pressure rating of the material?
No, no, it does not. What does improve the rating, the pressure rating, is the code working, right? So Super Shield helps maintain the performance while extending the service life of the parts that otherwise would see stress corrosion cracking or any type of hydrogen embrittlement much early on in the life of that structure or component or subcomponent.
Excellent. Thank you, Paula. Another question, what is the temperature range for Super Shield treatment?
There's no change in the temperature range in which the product can be used, if that's what the person who's asking the question is asking. Yeah.
Yes.
Excellent. We just have a couple more and a couple more minutes, so we're well timed here. Is there any concern with Super Shield and galling when it comes to bolts application?
So the way I would answer that is for our use cases that we have tested so far, there is absolutely no concern about galling.
Yes.
You know, that is why we are calling it a comprehensive solution, because it's a process. It's also based on the design of the product, which, you know, we are using the Parker robust designs for, you know, the product that we are applying this on. Yeah, there is no galling concern there at all. Yeah, that's where I would leave it.
Yeah, as a matter of fact, we're using the Parker technology as overall to deliver other performance enhancers like torque reduction, you know, anti-galling, or the ease of assembly of the parts. So there's more. And like I said, again, I don't want to be repetitive, but you can go to the white paper and read a little bit more about it. Go to our catalog where we're offering for our medium pressure products right now. But anywho, this is a solution that definitely, like Anshul said, delivers a comprehensive performance enhancer for all fittings.
And we're winding down here. Just two more quick ones. Is this a U.S. process, U.S. manufactured?
Correct, yes.
Okay. And one final, what is the effect on atmospheric CO2 in the process?
No effect.
Yeah.
Correct, Anshul? Yes.
Basically, yes.
Yeah.
Okay, well, we've hit that magical hour, Paul and Anshul, and I'd like to thank you for such a compelling presentation. And I have to be completely honest, I've never seen this many questions in a very long time. We had a very engaged audience that basically stayed with us the entire time. So thank you, Paul and Shul. Thank you for the audience. And this concludes the Parker Hannafin webinar. Following this session, anyone who signed up for it will receive an email with a link to the webinar for your reference.
Thank you
Thank you
so
very
much,
much.
Greg. Thank you.
Thank you. Thank you so much.
Thank you.